be a bit too dark. Is that better? Not sure.
Okay, I will now give the opening speech for the webinar. Okay, greetings everyone. Thank you for finding a time and visiting today's webinar with the title An Invitation to Model Theory. My name is Wang Kalun and I am the Secretary of the Logic Association of Malaysia. I will host the webinar today. Before we begin, I have a few housekeeping notes. Today's section is being recorded to be available for viewing post-conference. The recording will be uploaded to our YouTube channel. If you have any questions for the speaker, please use the chat feature in Zoom. Now, let me introduce our speaker. He is Associate Professor in Mathematics, working in the School of Mathematics of the University of East Anglia, Norway. His main research is in model theory and its interactions with algebra, number theory, and analysis. He has taught model theory at the University of Oxford, the University of Illinois at Chicago, and the University of East Anglia. He is also a writer of the book, An Invitation to Model Theory, which is the same title as the webinar today, and the book aims to bring model theory to an undergraduate audience. Without further ado, let us welcome our speaker, Dr. Jonathan Kirby.
Thank you very much, Juan, for that kind invitation, introduction. I see some more people just connecting, so I will start slowly. So thank you, yes, to Juan and to everyone at the Logic Association Malaysia for the invitation. It's very nice to be able to spread ideas about model theory to around the world. So thank you for the opportunity. Hopefully you can see my slides. As one said, this is the title, An Invitation to Model Theory. So I hope you feel welcome. Please do interrupt me. I have the chat window open, but I might not be looking at it. So if you do type in the chat, and I don't notice, perhaps someone can shout out, either one or someone else can let me know. Yes, so I am Jonathan Kirby. I'm working at the University of East Anglia, or UEA, in Norwich in the UK. And I've been here for about 13 years now. Previously, I guess I started my life in logic in the same place as your president, and doing a master's in logic in the University of Manchester. So, you know, it's got me this far, and I'm sure that's an opportunity which maybe is open to you in the future too, if you're interested by this talk. Okay, so my talk is briefly in 4 sections. The first one, I'm going to say a little bit about model theory and its position in logic. So this is a Logic Association in Malaysia, and I guess that everyone has some interest in logic, some background in some sort of logic, maybe propositional logic, maybe a bit more. But I imagine that most of you don't know much about model theory. So I'll try to explain roughly where it fits in logic. Secondly, I'll talk about mathematical structures, which are somehow what we study in model theory. One of the most important ideas in model theory is that of a definable set, or definable subset of a structure. So that's the third section. And another key idea in model theory is changing models. So we can think of a structure as a model of its theory, a model of the sentences which are true there. But we can change the model. If we have a theory, like the theory of groups, or the theory of fields, or the theory of of something else, a theory of set theory or something like this, we can change the model. We can start with some model and then move to a different model. And that's another of the key ideas in model theory. Okay, so I got you so far. Good. Right, so the first section is model theory in logic. So do let me know if you can, if this is clear, or if not, then shout out. So what is model theory about? As I said, so it's the ideas, we look at mathematical structures. We look at, as I said, definable sets. And I'll give some examples in a minute. And we look at different structures which, let me put this in inverted commas, look the same from the point of view of logic. In that they let me say, the same things are true about them. Maybe I put this in inverted commas as well. It's a sort of not precise mathematical statement. So how does that fit with logic? So maybe I could ask you, what do you think of logic? Can you give me some ideas that you think of when you think about logic? Anyone want to write something in the chat? The challenge. Logic gates, okay, so logic gates are things like AND gates, OR gates, NAND, NOR, yeah, good. So we will have AND and OR coming up, definitely. Anything else about logic? Well-formed statements with inference rules, thank you very much. Giving arguments correctly, good, yeah. Okay, so there's good things to start with. So in logic, these are all good ideas in logic. Let me look at well-formed statements with inference rules. So let me pick out that one. Okay, so what are we doing in model theory? So well-formed statements is absolutely what we're doing. We're going to have some formulas that are precisely syntactically specified. And this is what these formulas are going to be what defines our definable sets. So this is a key idea in model theory, it's well-formed statements. That's certainly that's mainly the key idea from logic we take. Inference rules. No inference rules in model theory. So in proof theory, yes, this is a very important part of logic, but not in model theory. So this is maybe one of the big distinctions. So often when people think about logic, they think about reasoning, inference, and formalizing that. And that's a different branch of logic. And so in model theory, what we're really concerned with is we have our formal language. So we have formal language. and we're interested in what we can express. What can and cannot be expressed in that language. So we're not so much dealing with inference, but with just what does the language tell us? What can we use the language for? So computer programs, someone's written computer programs in the chat. And again, that is very important. Computer programs, though, they're very much, you have a formal language, that's true. But there's more about inference, there's more about deduction. In a sense, there's the paradigm that says that computer programs are essentially the same thing as proofs. So that's closer to proof theory. Okay, thank you very much for those suggestions. So what can and cannot be expressed, and let me add something here, what can and cannot be defined. Okay, so that is basically what I mean by model theory. It's this sort of area. Okay, so let's move on. So let me give an example. So how do we express? We're going to express things about mathematical structures. So I'm going to move straight on to talking about mathematical structures. If I can spell it. Mathematical structures. So the example I'm going to have running throughout is the real field. So my notation for this is going to be, we have the reals. And yes, be careful with syntax. I'm going to put a semicolon here, although this isn't going to matter for the talk. And then we put, what is the language? What structure do we care about? So the real field, we've got addition, a multiplication, let's have subtraction, and a 0 and a 1. So this part here is the basic language, basic symbols of the language. And this part here is the underlying set of our structure, the domain of the structure. So what do I mean by this? I mean, we care about the reals and we care about the operation of addition, which is a binary operation, takes 2 arguments, and multiplication, again, takes 2 arguments, subtraction or negation, it doesn't matter particularly, you have to choose, but let's say the unary negation, which takes 1 argument, and the special elements 0 and 1, which play a particularly important role in the addition and multiplication. So we're going to take that as our structure. And what does it mean? So we can define certain things in this structure. So we can define, for example, let's say multiplication. So we've got multiplication already, but we can use, as you do in logic, you can use variables. So we can use x times y equals z. So we're always allowed to use the equal sign in our logic. So this is predicate. So I should ask, how many people have seen predicate logic before? Maybe you can, what can we do on Zoom? You can say, put your thumbs up if you've seen predicate logic before. Give me some idea of where to. So we've got 1. Oh, not very many. Okay, so I can explain it more slowly. So we're going to use these symbols, x, y, and z. So these are the variables. And we're always allowed equality here, equality. And this symbol is one of the basic symbols from the language. This is the multiplication. So this is expressing multiplication. So we're not defining multiplication here, because in the sense that we're not saying how to multiply real numbers. We're not giving a procedure. We're just assuming that you know that, and we're saying this is what we're going to be able to express in our language. So you can define addition like this and so on. What else could we define? So we could define multiplication. What else? We could define a set of squares. So a square number, so a square real number, what's that? It's the square of a real number. So how do we do that? We can use a quantifier. We can say there exists some z such that z times z is equal to x. So this defines the set of all x's in the real numbers, which are squares, right? Which are, there's some z times z is, so z squared is x. Okay, so what are squares in the real numbers? Anyone want to think about this? So what does a square real number look like? No, okay. So in the real numbers, this is the same as, yes, thank you. So Kokyung Hao has said positive reals. That's right. So, well, let me be a little more precise. I'm going to say non-negative reals. So 0 is a square, and I don't count 0 as a positive number. But yes, so this defines, so this is true of a point x, if and only if x is non-negative. Of course, we could take this same formula and evaluate it in the natural numbers or the integers, and then we get something else. Not all non-negative integers are squares of integers. So this quantifier is going to run over our structure over the reals, which is the same as where we're evaluating the truth here. So we can do the set of squares, and let me define another thing. So the usual linear order on the reals is given by what? So we can use this squares to define the usual linear order. So it's not in our language originally, but we can still define it. So we can say there exists a z such that z times z plus x equals y, brackets here. And that defines, what does that define? That defines x being less than or equal to y. Okay, because this z times z is some non-negative real number. And if there is such a non-negative real number that you add to x to get y, that's the same as saying x is less than or equal to y. So in a sense, when we look at this structure here, I'm saying these are the basic symbols that are going to be in our syntax. But if we allow this sort of abbreviation for this thing here, then we could also have less than or equal to, and sort of throw that into our syntax as a defined operation or defined relation. Okay, does it make sense so far? So we ask a question. There's a little bit of space here to ask an important question. Is the set of integers definable as a subset of the reals in this structure here? So any ideas? Any ideas? So we go yes. Okay, someone says yes, someone says no. Can we do a vote? I can't. Anyone willing to, let's say, can we have thumbs up for anyone who thinks yes, the integers should be definable? We've got 1, 2. Thumbs up now. Okay, 3, good. Okay, put your thumbs down. Now thumbs up for people who think it should not be definable. Three, 4. Okay, right, fairly evenly split. Okay, so let's, so this is not a trivial question. It's not easy to write down a formula which does define the integers. So of course, if we could just write down a formula, it would be easy to say yes. But how would you show that something is not definable? So that's let me ask this next question. How could we show that some set is not definable? And what even does it mean to be not definable or definable? So to make the question precise, we need a formal definition of definable. Okay, so we need a definition of definable. Okay, so this looks a bit circular, but that means that essentially it's not. This is where logic comes in. Right, so this is where our logic is important. So let me give this definition, and I'll give it for the example we have here. So we need a formal definition of terms and formulas in predicate logic. What's called predicate logic. So let's start with terms, and we'll stick with our example. So we stick with a language which is plus, times, minus, 0, 1. It's also called language of rings. So those of you who've done algebra should recognize that these are the basic operations of a ring: addition, multiplication, subtraction, 0 and 1. But if you haven't done any algebra, that's okay. You know what these things are in the real numbers. So, and that's all we really will use today. Okay, so we start with recursive definition of terms. So terms, start here. So this is so what do we have? A variable is a term. So variables are x, y, z, x1 or something like this. So I guess we should, if we were working in a programming language, we'd need to specify exactly which syntactic things are terms, but which things are variables. But let's just leave it as a little bit unspecified here, but there shouldn't be too many of them. It should be countably many of them. So you can have x1, x2, and so on, but that'll do. Okay, so 0 and 1 are special constant symbols of this language are terms. Strictly speaking, terms of the language L ring, language of rings. And now we have some recursion. So if you do programming, you'll be happy with this sort of construction. So it says if T1 and T2 are terms, then let's say minus T1 and T1 plus T2 and T1 times T2 are terms. Okay, so this is a definition by recursion. We're defining terms in terms of terms. And hopefully that idea is not mysterious to anyone. So let's give an example. So we can start with 0, we can add x, we can multiply by y plus 1. I'll put brackets around that, brackets for this one, and something like this. So we can put a minus sign in front, or brackets. Okay, so there's an example of, we built this up with these rules. Okay, so these are terms, and you can see they sort of represent functions. So if you've got variables in x and y, you could plug in those and evaluate them, and you get a number. So terms represent functions from R, let's say maybe R to the n, if you've got n variables, here are x and y, so 2 of them. And then, so back to the reals. Okay, is that okay? People happy with this? So as exercise, I set my students. So in this language, what sort of functions do you get? And can anyone see another name for the sort of functions you can get this way? It's quite a hard exercise if you haven't seen it before. Okay, so in this case, what you get are things called polynomial functions. So let's say polynomial functions. In this case meaning this language of rings. Okay, so those are terms, and they're built recursively. So terms are just functions. They're not things which are true or false. They're just functions. But formulas are going to be true or false, and they're going to be what define our definable sets. So formulas. So again, we have a recursive definition. So if T1 and T2 are terms, then T1 equals T2, brackets like this, is a formula. Okay, so we can say that 2 functions take the same value, or that 1 function is equal to 0. And that's a formula. Okay, so we can say x times x plus 1 equals 0. And that has no solutions in the real numbers. It's plus and minus I would be our solutions in the complex numbers, but That would be an example of a formula, and it has a free variable x times x equals +1 equals 0, and it's going to pick out the values of x for which that's true. So it defines a subset, which in this case is empty. Okay, so that's, and then we build them up recursively. So we get if, let's see, T1, no, I don't want terms anymore, I want formulas. So if phi1 and phi2 are formulas, so are not phi1. So this is the negation. So here are logic gates coming in. Phi1 and phi2, with brackets. We need the brackets to make our syntax work. Phi1 or phi2. We can say phi1 implies phi2. Okay, so hopefully these symbols are familiar, but if not, let's just write some names. So this is not, this is and, this is or, and this is implies. Okay, so this is where the logic, hopefully people are reasonably familiar with this level of logic gates, logic operations. And there's one more thing, which is quantifiers. So if phi is a formula and x is a variable, so any variable, then we can have there exists x, phi, and for all x, phi, are formulas. So these are the quantifiers. Are these symbols familiar? Maybe people can, someone let me know that these for all and exists symbols. Yes, most people know these or not? Yes. Okay, okay, good, thank you. Okay, and these are all the ways we produce formulas. So maybe I should give some, so the key ideas here, maybe this is a recursive definition. Such as you would get in programming. You build up expressions, regular expressions, or expressions from smaller expressions in programming. But it means you've got a precise control of what is and is not a formula. So maybe I should add, there's an important clause which I didn't write. So nothing else is a formula. Okay, so we've got our starting point, we've got our rules for building new formulas from formulas, and that's it. Okay, so let me move on a little bit, and I say, so a definable set has a definition. So a subset of, let's say, r to the n is definable in this, with respect to this structure. So maybe just to be clear in the language of rings here, if there is a formula phi, I'm going to write it with variables here, x1 to xn, so these are the free variables with so-called free variables, so not quantified variables x1 up to xn, or I should give names, so it's a subset, let's say S, such that A1 up to AN is in S if and only if the formula phi is true when A1 up to AN are substituted for the variables x1 up to xn. Okay, does that make any sense? If you've seen it before, it will make sense. If you haven't, I don't know, it might be a bit fast. So I should give an example. So if we take the formula that we had before, there exists a z such that z times z equals x. So this is our unquantified variable here. So there's only one of them. So this defines the subset of R with only one, so R to the 1, if you like, but I don't write the 1. So it's what? It's a subset, the set of X in R such that X is greater or equal to 0. Okay, so that's a subset. We can always draw a picture. So let's draw the real line. Here's 0, here's 1. And that's the subset. This is the subset which is defined, this part of the line. Oops. Okay, so let's give another example. So example 1, example 2. So let's take a formula with, let's say, 2 free variables. So we can take y plus 1 equals x. So there's a formula in 2 variables, now x and y. And well, if we write x and y axes, the set of points where that is true is, so x is y plus 1. So we've got, say, if we have 1 here, here's minus 1 on the y-axis. So this is going to be the straight line through these 2 points. So this line is defined by that formula. So it's a subset of the plane. Okay, so, and we can define more complicated things. But let's go back to the original question. Can we define the set of all integers? Okay, so hold that thought. So now we know we've got a definition of what it means for a set to be definable. And the example today, I'm just using this language of rings with this real, the real field. Of course, you can apply it to many other structures. Any mathematical structure you can think of, pretty much, you can apply model theory to. But for today, let's just stick to this example. So let's think about, so what sets are definable? So here's an observation. There's another bit of logic. So R is an uncountable set. So by Cantor's diagonal argument, it's not countable. Formulas are finite strings of symbols from a countable from a countable set of symbols. Okay, so there are only countably many of them. So there are only countably many definable sets. Well, let's say definable subsets of R, or of Rn for any n or even all n. So the collection of all definable sets is countable. But R is an uncountable set, so R has uncountably many subsets. In fact, it has 2 to the 2 to the aleph naught, so it's the number of subsets is large. It's even larger than the number of real numbers, 2 to the continuum instead of just continuum. So what does that mean? It means that most most subsets of R are not definable. Okay. So that's just a bit of logic, a bit of elementary set theory. Just counting argument says that most sets are not definable. So definable sets are very special. Maybe they're the sets we care about, but they're certainly not every set. Now, what we could do if we say, oh, we want to define something different, we could just expand the language we start with. And so if you want a set to be definable, you can sort of put that into the language to start with. But that, you know, that does in some sense that can be very useful because one wants to study other mathematical objects, and maybe you want to study the exponential function, for example, is something I study a lot. So you sort of put that into your language to start with. So you don't just have addition and multiplication, but also exponentiation. But then you still have lots more things which are not definable. So that's so certainly that's true. But how can we tell? What is not definable? Okay. So we're going to have a method. So a method called automorphisms. So here, automorphism is an idea from algebra. And we're going to bring this in to you to show that some things are not definable. But I'm going to illustrate this with a different example. So we're going to take a slightly different structure. And the example is still the real numbers, but now not as a field. So we're going to take the real numbers, and we're going to take addition. Let's have subtraction as well, and 0. So it's R as an additive group. So again, if you've done algebra and you know what groups are, you'll know this, you'll recognize this. If you haven't done algebra, that's okay. You know what addition of real numbers is. So that's all we're going to use. So here's a question. Is the linear order definable? here in this structure. Okay, so let me ask you, so let's have thumbs up again. Thumbs up if you think it is definable. Anyone who thinks it is definable? No one. Okay. Oh, yes, good. We've got a couple. Good. Okay. Thumbs down. Thumbs up again if you think it's not definable. More thumbs. A few thumbs here. Okay, so let's remember. Thank you. So in R and with the ring language, this is definable by the formula there exists a z times z plus x equals y. So this is what we had before. But of course, here we're using multiplication. So multiplication we don't have anymore in this structure. So this formula certainly doesn't define linear order in this structure because it's the wrong language. But maybe there's another formula which defines the order. But in fact, there isn't. So in fact, there is no additive group formula. There is no such formula in the language with just plus, minus, and 0. So how are we going to prove that? Well, we need an idea, and the idea is to use this method of automorphisms. So here's what we're going to do. Consider the map function, if you like, the map from the reals to the reals, which takes a real number a and maps it to minus a. Let's call this map pi. Okay, so pi, if you like, write it this way, pi of a equals minus a. So pi is a bijection. So it's an invertible map. In fact, it's its own inverse. If you do it twice, you get back to the identity map. And what else do we know? Well, pi is going to preserve. Pi preserves 0 and plus and minus. So what does that mean? So we've got pi of 0 equals 0. Yeah, minus 0 is 0. And for, let's say, a and b in the reals, pi of a plus b is, well, it's minus a plus b, which is minus a plus minus b, which is pi of a plus pi of b. So we can do first plus and then pi, or we can do pi separately and then do the plus. So that's what we mean by preserving addition. And we also have pi of minus a equals minus pi of a. Okay, so that's easy to check because pi is just the same as minus. So this is minus minus a. So both of these are just minus minus a. Okay, so what we've got is a bijection which preserves all the things in our language. So our language here, plus minus 0. So a bijection from a structure to itself, which preserves these things, is called an automorphism. Okay, so pi is called an automorphism of the structure. So I guess you might, if you've seen this word, you might, if you haven't seen this word, you might have seen the words isomorphism. I hope if you've done any algebra course, you've seen the word isomorphism. And isomorphism is something which preserves a structure, but maybe moves one structure to another, like a group to another group, or a field to another field, a ring to another ring, or Banach space to another Banach space, or something like this. But that's an isomorphism. An automorphism, auto just means self, so it's an automorphism, an isomorphism from a structure to itself. So, and here's, but how does pi relate to the linear order? So pi does not preserve the linear order. What does it mean? Well, for example, we have that 1 is less than or equal to 2. But if we do pi of 1, that's not less than pi of 2. Why? Because pi of 1, so pi of 1 is minus 1. That's certainly not less than or equal to minus 2, because minus 2 is less than minus 1. So that's what we mean by pi not preserving the linear order. In fact, it swaps it over. Okay, but what we need now is a lemma. And the lemma says, if A is any structure, S contained in A to the n is a definable set, and pi is an automorphism of A, then pi of S equals S. So in other words, so this is some algebraist notation, but let's make it clear. We have a tuple, let's say A1 up to AN belongs to S if and only if A1 up to AN, sorry, that's pi of A1 up to pi of A1 up to pi of AN, so we apply this to all of those things, is in S. So in this case, we've got the pair 1, 2 is in the linear order, so it's in the set of, where less than or equal is true. But pi of 1, pi of 2 is not, because pi of 1, pi of 2 is not. Pi of 1 is not less than or equal to pi of 2. So applying the lemma, so this thing is not definable. In the reals with just the additive group structure. Okay, it makes some sense. So we now have a method for showing things are not definable. Happy? Good, thumbs up. Right. Now, this method is not infallible. So what about, oh, I should maybe say something about the proof of the lemma. Okay, so this lemma so we want to know why things are true. We should prove them. How is it proved? Well, it's proved, I'm not going to do the whole proof, but I'll say it's by induction on the recursive construction of formulas. Okay, so definable sets defined by some formula. And what we need to know is that the truth of a formula at a point is preserved under automorphism. So if you move the point by an automorphism, that formula, and you've got a formula which is true originally, that's still going to be true when you move the point. And that's true for the basic for the basic things, the terms, because that's what it means to preserve. That's what it means to be an automorphism. So you preserve all the symbols in the structure, the plus, minus in this case, and 0. And then you can just show that, well, and or and not, these things are also preserved. So you've got to do inductions for these. And the slightly harder is the quantifiers, the for all and exists. It's not very hard, but that's the idea of the proof. Okay, how am I doing for time? It's 5 to 11, so about half an hour left. Okay, so that's the idea. But as I said, this lemma is not it is not infallible. We can't always use it. So let's go back to the question. What about defining Z in R with a ring structure? So we want to show it's not definable. So I'm giving that to you now. It's not definable. But how could we show it? Well, we could hope to find an automorphism of this ring structure which doesn't preserve Z. But actually we can't do that, because in fact this thing has no automorphisms. Okay, except the identity. So the identity map just sends everything to itself. That's obviously an automorphism, but it's not useful. We can't do anything with it. So that's no good. So we can't use the lemma. At least we can't directly use the lemma. So there's something we could do, which I won't do today because it's a bit more complicated. What we can do is we could change the model. We can start with our real numbers, change the model to a much bigger model, which does have automorphisms, and then show that we get an automorphism. But however Z were supposed to be extended to our bigger model, it wouldn't work. You know, we'd be able to move it with an automorphism, or move a point that should be in Z to something which is not in Z, and then come back down again. But I'm not going to do that. That's too hard. I'm going to have to think about some other methods. So we need another idea. So we need another idea. So what's the other idea? So the other idea is quantifier elimination. What's quantifier elimination? Well, formulas are made up of, they're built up from our basic symbols and a logical operation like and, or, not, and quantifiers for all exists. And by and large, the basic logical operations are really easy to understand. There's Boolean operations, and or not. So you all understand this. You understand, you know, how you build things from these things. But quantifiers, maybe you understand how to do it, but they're much harder to get a grasp of what's definable with these quantifiers, especially if you've got lots of them. So if we just say for all x, x is greater than 0 or something, I mean, this is quite easy to understand. But if I have lots of alternating quantifiers, like for all epsilon greater than 0, there exists a delta greater than 0 such that for all x and y, the distance, if x minus y is less than 5, less than delta, then x squared minus y squared is less than epsilon. This is rather a long thing. It's hard to understand. I mean, that's expressing something like continuity of the squaring function. So if you've done some basic analysis, you will have seen things a bit like that. But you know that if you do analysis, it takes quite a lot of getting your head around these ideas with 3 alternations of quantifiers. And well, if you have, once you have 4, 5, 6 quantifiers all alternating, then you can sort of forget about trying to understand what it really means. It's really complicated. So quantifier elimination is an idea of let's just eliminate all the quantifiers so we don't have to worry about that complexity. And sometimes we can do it. So here's a really important theorem. This is due to Tarski. And maybe also Seidenberg. And it says, in the language, in the reals, with the ring language, as we started with, if we add the order to the language, so remember, we can do that in a sense because that was definable by this formula with a quantifier. There exists z times z. There exists a z such that z times z plus x equals y. It defines x as less than or equal to y. Then every definable set, every definable subset of R to the n, for all natural numbers n, is definable by a formula without quantifiers. Okay, so that's maybe surprising, but it's a really important theorem, and it really says that the definable sets in this structure actually very simple. Now, that's and it's really, really useful. And these definable, well, I say they're simple, but they're not. They're still very expressive. So any sort of polynomial equations, or the graphs of y equals x squared and things, and you've got less than or equal to, so some box or something cut out by polynomials, curves and things, these are all definable. So these are so-called semi-algebraic sets, defined by inequalities of polynomial equations, inequalities and equations of polynomials. But nonetheless, what's really important in model theory is that nothing else is definable in this language. So this is a very powerful expression. So let's give an example. So I'm certainly not going to give a proof of this. It's quite hard. In fact, this theorem itself is a little bit too hard to prove in my my introductory book on model theory, but it is proved in other introductory model theory books. I prove a similar theorem for the complex numbers, which is the proof is a bit easier. So let's do an example. so if we take, so in the reals, let's do something that you hopefully know. There exists an x such that a times x squared plus b times x plus c equals 0. Okay, so this is a, so a, b, and c are our variables here. X squared means, of course, x times x. So I write this as an abbreviation. So this is a formula. So this is a formula. It defines some subset. So it defines a subset of r cubed. So we've got these coefficients of our quadratic equation. And we define a subset of r cubed where the set of coefficients where that quadratic equation has a real solution. So anyone know another way of defining that set? So when does a quadratic equation have a solution, a real solution? So this I hope you've seen at school or somewhere. Now, have I lost everyone now? Ah, someone's replied. Good, good. Yes, excellent. We've got some in the chat. Good. Yep. So the discriminant, which is, as two people have said, it's exactly. So this defines a subset of r cubed, and it's the same subset as, yes, b times b, let's say is greater or equal to 4 times a times c. Or just maybe if we want to just really to make that a formula, we can say b times b is greater or equal to 1 plus 1 plus 1 plus 1 times a times c. So that's really a formula in our language with greater or equal to here. Yeah, but of course, normally we don't write out this 1 plus 1 plus 1 plus 1 like this with brackets and everything. But just to make it actually a formula in our language, we at least should be able to see that we can do that. So there we go. We've got eliminated the quantifier from here. And this is then much easier to understand. So we've got, okay, it lives in three-dimensional space, but it's some sort of surface in three-dimensional space that we could plot on a computer and we'd know what it is. Whereas this, with the existential quantifier, well, we've got 4 variables. We've got the x variable as well. So we're in 4-dimensional space, but then we have this existential quantifier, which is then projecting down to 3-dimensional space. And it's really hard to understand just what that looks like, except by eliminating the quantifier and getting this discriminant. Okay, so there we go. That's an example of what quantifier elimination means. We've got something which is potentially a bit complicated, and we simplify it. And the theorem of Tarski is that you can do that for any number of quantifiers. You can get rid of all of them. Okay, so there are 2 different proofs of that. Tarski's original proof is syntactic. So he gives an algorithm for eliminating the quantifiers. And the modern proof is more semantic. We deal with real closed fields and extensions of real closed fields and some, and it's really much more model theoretic, a very different sort of idea. And you could read about it in my book, but I don't have time to explain it. Okay, so that's an example of quantifier elimination. So let's give a corollary. So a corollary Z is not definable in the ring language. And the proof again, I can't quite give all the details, but it's enough to show it is not definable without quantifiers. But in the language with the order. So that's the immediate corollary of the theorem, Tarski's theorem. And then we show by induction on quantifier-free formulas that every definable subset of R in one variable is a finite union of points and intervals. So you have your real line, and on it you can name some points. Maybe you can name 1, 2, -5 things you can name, and you can also name intervals. So so the interval from 1 to 2, we've got 0, -2, -3, whatever. So you can name. It's easy to express all of these things with quantifier-free formulas. So x is greater than 1 and x is less than 2 would give you this interval here. X equals 0, x plus 1 equals 0, or x plus 2 equals 0, so on. So you can do this. Using the and or, you can get finite unions of these things and intersections of them with and finite Boolean combinations of them. But you can just prove without too much difficulty that these things will always be finite unions of points and intervals. And then of course Z is not, because it's infinite, well, it doesn't have any intervals in it, no real intervals. So it's not a finite union of points and intervals. So that's the idea. So if you're given Tarski's theorem for quantifier elimination, then it's not a big job to prove that Z is not definable, to prove this idea. Okay, but it does go beyond the basics of logic. You've got to really understand something about real numbers and polynomials and elimination theory, or something about real ordered fields. So one way or the other, you have to do some quite non-trivial mathematics to prove this. Okay. Any questions about anything I've said so far? No questions. Okay, so let me move on to the last topic I want to talk about. So if you've been lost, then come back. So the last section is on the change of models, changing models. Okay, so what do we have here? So in model theory, we start with some structure. Let me be slightly more abstract here. So we start with a structure A in language L. So we had our real field in the language of rings. And so we can take TH of A, the theory of A, is the set of all formulas in our language, so L formulas, with no free variables. So you build it without variables or with variables, but then you have to quantify over all the variables. So you get some, so these things are called sentences, which are true in A. Okay, so a formula, once you take a formula and you plug in elements of A for all the free variables, or if you have no free variables to start with, then you get something which is either true or false in your structure. So we just take everything which is true, and we're going to call that the theory of the structure. And so there's a key idea. So we say, okay, we need to know what the word model means. We call A model of its theory. So a theory of A is a set of sentences, but then you can also take some other theory, like the theory of all groups. So group theory is the study of the theory of groups, ring theory, whatever. So the theory of linear orders, theory of sets. So, so something for which everything in that theory is true is a model of that theory. So this is the word model in model theory. It's the setting where everything you want to be true is true. At least, well, okay, for appropriately chosen things that you want. Okay, so the key idea is that there will be, at least if A is infinite, so in other words, has infinitely many points, the underlying set is infinite, like the real numbers, but not like a group of order 4, not like a finite cyclic group or something. So an infinite set, if A is infinite, then there are many other models of its theory. Okay, so we can change to a different model, and then we maybe can prove things about the other model, and then maybe we can pull those things back to the model we started with. So how do we get these models? So there are two main theorems about these. So, so the main theorems are called the upward and downward Lowenheim-Skerlam theorems. Okay, so Lowenheim and Skerlam are two mathematicians. And I'm going to talk about the downward one. But these are the main ones. So the theorem, the downward Lowenheim-Skerlam theorem, says this. So let's take B, let's use a normal script B. Let B be an, let's say, uncountable. Countable is okay, but then it doesn't, the theorem won't tell us anything. So there'll be an uncountable L structure. So this is maybe not quite the full generality. So I'm going to restrict to the, so, well, let me just write it, and then I'll tell you in what case it's not quite full generality. then there is a countable L substructure. Let's call it A of B. So we have A contained in B such that, okay, so the theory of A is equal to the theory of B. So this is not quite the full generality. The theorem tells you a little bit more, but this will do for us. And I guess I should come clean on one thing. So sort of countable. So L should be a countable language to start with. So remember when we start with the language we looked at had plus, times, minus, 0, and 1. This is just finitely many symbols. So you could have countably many symbols to start with if you wanted, that's fine, but you shouldn't have uncountably many, because then this theorem might not be true. But you still get a variant. I mean, you still get something very similar, but just maybe you can't come down to countable. So for example, if you named every real number with its own symbol, that would be an uncountable language, and you can't get anything smaller because you need all of those numbers. The theory said that they're all different. They're not. If A and B are different real numbers, and you've got symbols for A and B, the theory will say that A is not equal to B. So you can't do that with uncountably many symbols. But then we're doing logic, and you can't write down uncountably many things anyway. So that's fine. Okay, so there's a countable L structure. So in particular, so application, there is a countable R, curly R in the real numbers. So an ordered field, because being a field is part of the theory and being ordered is part of the theory. Whether the order is in the original language or not, it's definable. So that's not difficult to prove. And the rational field is contained in the reals. It's countable. It's ordered, but which behaves exactly like the reals as far as, so it's indistinguishable from the reals as far as first order logic predicate logic can tell. Okay, so what sort of things can you say in this first order predicate logic? So e.g., what real numbers do we have? So we've got, for example, in R, the formula, the sentence, so sentence is a formula with no free variables. The sentence, there exists an X such that X times X equals 1 plus 1 equals 2 is true. So the square root of 2 is in other words, the square root of 2 is in the reals. So the square root of 2 must be in this curly R. So R is not the rationals. So it can't just be the rationals. You've got to have the square root of 2. And similarly, if P of X is a polynomial, let's say over with integer coefficients, with a root in with a root in R, then the root is also in curly R. But in fact, that's enough. So we do not need E and pi in curly R. So that, you know, the exponential E, base of the natural logarithm, 2.7, so on, and pi 3.14, so on. We don't need, they don't have to be, they're transcendental numbers. They don't satisfy any polynomial equations. And it turns out that you can't express things like the circumference of a circle in this language, or exponentials and logarithms. You can't express them, and so you don't need these numbers. So in fact, so we have this algebraic idea of algebraic numbers and a real closed field. Okay, maybe this is just some words to you, real closed field. So it's, but this is, so this is the theory of, so the theory of the reals in a ring is a theory of real closed fields. So I encourage you to go away and look up that and see what it is. But what's mysterious here is, I hope you think it's interesting, mysterious, is Cantor's theorem, one of Cantor's theorems, says that reals are uncountable. Set of real numbers is uncountable. Hopefully that's familiar. So it has this diagonal argument with decimal numbers, and you try and list them all, and then you can change you can find a new decimal number by changing the decimal that you have, the digit you have along the diagonal, and you get a new decimal number, which is a real number that's not on the list. So your countable list can't have been everything. So they're uncountable. But here we've got a countable version of the reals. Okay, it's just like the reals as far as you can see, except it's countable. And that idea is really important. And let me finish with one more application. Another application of the Downward-Lowenham theorem, and this is an idea in logic. So another branch of logic I haven't talked about is set theory. So ZFC axioms of set theory. So a model. So let's take a model of that. So model is usually written V with a set membership. So it's a universe of sets. So the universe of all sets is a model of ZFC set theory, Zermelo-Frenkel set theory with the axiom of choice. So ZFC says, so one of the things that follows from it is there exists an uncountable set. Okay, so this is true in Zermelo-Frenkel set theory. Well, in fact, almost any theory of sets, the theory of a universe of sets. So it doesn't have to be ZFC, but that's the usual axiom. So there exists an uncountable set. So there is some set S in V which is uncountable. But all elements of S are also in V. Okay, so this is what it means. I mean, the elements of S should also be in V. That's what it means for V to be the universe of all sets. So V has uncountably many elements. So what does that mean? V is uncountable. But by the downward Löwenheim-Skolem theorem, V can be countable. Okay, so we said that V has to be uncountable, but actually it can also be countable. Okay, so the challenge is to explain. Excuse me, explain this paradox. Okay, so I think I'm going to leave you there with a paradox and say thank you very much for your attention.
Okay, thank you, Dr. Jonathan. So I think now should be Q&A sections. So are there any questions for the participants? Any questions to ask?
So I hope I haven't lost everyone. I hope
Can you say a little bit about?
It's supposed to be fun anyway. Sorry?
It's a fun talk.
Thank you. Thank you.
Yeah, can you say a little bit about how model theory can be applied to analysis, algebra? I mean, for the PhD students who are working on algebra and analysis.
Yes. Okay. So so let me say something about so differential equations. Let me say something about differential equations first. Okay, so this is I mean, this is somewhere in analysis, but what I'm thinking about is algebraic differential equations. So a differential equation that you can write, so say a polynomial in some functions. So like the heat equation, the dispersion equations, partial differential equation, or Fuchs equations, or Picard-Vecchio equations, or many equations which come up in physics or whatever are polynomials in some explicit formula, explicit functions. Okay, so what can we say? So we can look at these model theoretically. So what we do is we look at them in as sort of algebraic objects, even though we're thinking of, you know, their solutions. This is really some bit of analysis. But we can also look at them as algebraic objects. And then we can study them in the model theory of differential fields or differential algebra. And we can do things like, suppose you have two different solutions to a differential equation. Must they be, so if you have a linear equation, you know that different solutions are related by constants. So in some sense, you've got a vector space of solutions. So this is a linear equation. If you have a nonlinear equation, it's not so clear. And you can ask, well, if you have two different equations, two different solutions to my equation, how are they related to each other? Maybe if you've got one, you can get another one by some algebraic operation. And so there's some recent work in model theory by some, well, several people, Freitag, Naglu, Casal, other people I remember this, but there are others. And they prove for many important classes of equations that that actually this infinite set of solutions you get to this nonlinear equations have no algebraic relations between them at all. So that's quite useful in the study of these, certainly in the abstract study of these differential equations, and potentially in physics. For example, it tells you that if you have you solve this equation, so you've got some, let's say, trajectory for your particle, and you want to know, is there something else which is going to resonate with it harmonically or something? So you might get some interference, and this proves that this can't happen. You can't have two solutions which are sort of different solutions but close to each other, or satisfying some sort of resonance. So this is model theoretic proof, and maybe I can't really explain how it works or exactly how it goes, but there's an example of application to analysis. In algebra, there's an old theorem of, let's say, Wanda Shmilev, Russian model theorist roughly in the 1950s, I think, and she was looking at commutative groups. So there's a question of, I'm trying to remember exactly. So I think it's, yeah, if you're looking at abelian groups, commutative groups, and you want to classify the theories of abelian groups. So let's say, yeah, so I can't remember it quite full generality, but so she classes. So if you have, say, a divisible abelian group, which is, so it means that for every non-zero, well, for every natural number n, you can always divide any element by n. So for example, the rational numbers under addition, these are divisible. Then you could look at the torsion. So that's the things which you can add to itself a certain number of times and you get back to zero. So you can count for every natural number n how many elements of n torsion are there, and you can express that in a theory, in the theory. So in the language of groups, you can express that. So, but if you do that for every torsion element, then, if I remember correctly, that is no, okay. And then you also need to know, if you quotient out by the torsion how many cosets do you have, something like this, then you can put that in the theory as well, and that gives you the complete theory of these abelian groups. And so you get a classification. So the first order theory tells you it tells you a lot about classifying all of these. In particular, for countable ones, it'll tell you you can classify all the countable abelian groups. And this is a model theoretic application to algebra. So that's quite old. That's reasonably straightforward, but that's the sort of thing that exists. Does that help?
Yeah, thanks.
Yeah, otherwise there's lots more things to geometry, to algebra. So I guess let me do an advertisement for my book. It's an invitation to model theory. So in here, it is aimed at undergraduates. So if you like what you've heard today, do find a copy. Maybe your library has one, maybe it doesn't, but you can buy it online. And apart from the theoretical things, I try very hard to make sure there are examples. So I do the complex field, the real field, as I talked about today, and linear orders, Boolean algebras, vector spaces, things like this. And at the end, it's in 6 parts, and the last part, I don't know if you can see it here, part 6 here is on algebraically closed fields. So the theory of the complex field. And the definable sets there correspond to things called algebraic varieties, which are the basic objects in algebraic geometry. So yes, indeed, in the chat, get your libraries to buy a copy. Please do. And one can, algebraic geometry is a sort of study of geometry of polynomials, and it's a really, and this is where the connection is, definable sets of polynomials. And this is, I think, where model theory has made a lot of contributions in algebraic geometry, and also the applications to number theory. But maybe it's a little bit hard for me to explain in too much detail how that goes. It's a subject for many more talks.
Okay, thank you, Dr. Jonathan. Any other questions from other participants?
Ali has one.
Okay, can you hear me?
I can hear you, yes.
Very well. Thank you, Jonathan, for your nice presentation. My question is about the title of your talk, Invitation to Model Theory. But we know that there are different types and trends in model theory. For example, you have applied model theory, you have style set theoretic model theory, you have McIntyre style model theory, and these don't seem to be compatible with each other. Well, my question is, okay, if someone accepts your invitation to model theory, which branch of model theory do you recommend?
That's a good thing. I mean, these different branches of model theory are certainly compatible, but they may not, I mean, and you find interesting overlaps between them, but certainly you can't learn everything. It's much too big a subject for anyone to learn everything in model theory. My view is that to start with, you should learn, certainly you have to learn the basic theory. Everyone has to learn what are languages and structures and the compactness theorem and the Löwenheim-Skolem theorems I talked about, and a little bit about types. And the other thing I think you need to do is you need not just to learn it abstractly, but to learn these things with relation to some examples. So you see what they really mean in applications. They're not just abstract, meaningless things. You have to understand that these things come out of the study of fields or the study of groups or something. These things have a meaning. And so that's what I try to put in my book. The focus I put in my book is on definable sets, because I think that is the idea which is, first of all, easiest to grasp, because it relates to things like graphs of polynomials and things that everyone has seen at some stage. And it's also, I mean, this applications in number theory, a lot of them really relate to definable sets. So it's a key idea that is really used. So I think probably everyone should start here and learn these basics. And this is what I threw into the book. And the example of algebraically closed fields is a key motivating example for so many developments in model theory. So I think this is the place to start, which is why this is what I put in the book. There are other things, you can do other things. I haven't talked about sort of probability ideas. So that there are connections with limiting probabilities, 0-1 laws and things in combinatorics. And that is another sort of direction, but I think you still need to understand formulas and things. So, so that's my take. And then once you've learned the basics, you can certainly go into McIntyre direction or as number theory direction, or just into pure model theory. But I don't think you should do pure model theory without understanding some basic applications, and I don't think you should do applications without understanding the basic theory. So I hope that answers your question, Ali.
Right. My question is actually from
I can't hear you now.
Can you hear me now?
Yes.
Oh, yes. My question originates from discussion between McIntyre and Horoshovsky back in the days, where McIntyre didn't believe in Horoshovsky style stability theory and his constructions, and I guess there were some discussions inside model theory on what to do next and which project or approach should be taken by the researchers. So that's actually a big divide inside the model theory community, I guess.
There was a big divide in the 1970s, 1980s in model theory between the theoretical side and the applied side. But that I think that's gone. I really believe that's gone. And I was sitting next to Angus McIntyre last week in Oxford in a conference, and Udi Hrushevsky was there as well. So I chatted to both of them last week. I can assure you that they're on perfectly good terms and they're not arguing. I mean, the big thing is that some of these ideas from pure model theory, these technologies that seemed very abstract and very obscure, turn out to have big applications in other bits of mathematics. So so McIntyre was originally focusing on following Abraham Robinson in sort of looking at maybe not high-tech model theory, but the definability, as I talked about it today, in various structures, like for McIntyre, particularly p-adic fields, and this differential algebra and things. But it turns out that, you know, this more abstract model theory with types and ranks and stability and things, which you may have heard of, turned out to be really useful. And Udi Hrushevsky made some spectacular breakthrough using quite sophisticated ideas in stability theory and ranks, rank notions and things, using very abstract combinatorial model theoretic ideas. And he proved some theorems in number theory, in geometry, this Mordell-Lang, function field Mordell-Lang conjecture, and in positive characteristic of things. And then more recently, some really deep results in geometry, algebraic geometry, Berkovich spaces and things that Hrushevsky has done, which are very deep model theory, very difficult deep model theory of valued fields. And then again, this theoretical development of O-minimality, which is definable sets in the real field, like I talked about, but also where you allow some analytic structure. These have had very deep results in model theory, in number theory, this Peeler-Wilkie method. But it uses some sophisticated model theory. So you can't do it with this naive, with just to the application side. You need to understand the deep, pure model theory to get the applications. So these two areas are really much more linked now than they were maybe 30, 40 years ago.
Very nice.
So,
thank you very much.
You're welcome.
There's a question in the chat. Can you take a look?
Yes, what have we got? Why isn't the equal symbol defined? So this is just a convention. So the convention in model theory that is equals is a basic symbol in your language. So you always have it in every language. So you don't bother to write it for a specific language. But I know that's just a convention. Model theory without equality is somehow not what we do. It's not so useful. But I mean, there is predicate logic without equality, which people in philosophical logic use. But it's anyway, but we don't, because it's not so useful for the sort of things that we want to do.
Yeah, I'm interested in what you just said about the model theory and probability. Are you working on those, or?
I'm not specifically, no. There's a book by Spencer, I think, called The Strange Logic of Random Graphs, or something like this, which has a lot of development in this direction. I think the book is probably 30 years old now. And this contains a lot of ideas in that direction, and that area still exists. People do look at that, and that's closer to computer science.
Oh, yeah.
In some ways. So typically what you look at is a collection of finite structures, maybe graphs, for example. And you look at so certain graphs, and you're looking at what happens to this in this family of graphs as graphs get larger. So you're looking at some sort of limit behavior within that family as the size of the graph goes to infinity. One model theoretic way of doing that is to take an actual limit to infinity, which you do with ultra products, or you can do it other ways, but this is one way to do it. And then to study these infinite things, which sort of behave like limiting objects. And you turn out that, for example, what you often get is that the probability of some behavior happening, like the probability of your graph being connected, is going to go to 0 or 1. It's not going to go to a half or anything in between. It's going to be either 0 or 1. Oh. Because it depends on your family of graphs being nice enough to start with, but typically this happens. This is a sort of question yeah, but I'm not very expert in that.
What's that area called? Is it model theory of graphs or something?
One thing I guess to look at is the pseudo-finite structures.
Okay.
Pseudo-finite. And another thing to look at would be random graphs. Random graphs. So yeah, so anything slightly deeper theory of random graphs, or random hypergraphs, or random something. So yes, pseudo-finite structures, random graphs. Thanks in the chat. Yes, that's right.
Yeah.
Okay, any other questions from other participants? Okay, if there's no questions, so this will conclude the webinar. So just as a reminder, please click the link in the chat and fill out the Google form to get the e-certificate. And the e-certificate, it will be distributed within 2 weeks. So thank you all for attending. We hope you have learned and enjoyed this webinar. And thanks again, Dr. Jonathan, for your nice presentation.
Thank you very much, John.
Thank you very much for the invitation. It's been fun.
It's been fun, yes.